Hello, I'm Pierre-Peter Longo, working at INRIA, and I want to talk about the quotient filter. So, what is a quotient filter? Quotient filter is a data structure that appeared in 2011 in this paper, and it's what is called an AMQ. AMQ means approximate membership query. And AMQ are data structures that are low, have a low impact in memory, but can have some false positives. This means that if you ask something to an AMQ, if the answer is no, this means no, and if it's yes, it means maybe. There can be some false positive. What is a quotient filter? Basically, this is a simple bit array slided into some slots, what we call slots here, and one slot has 3 bits plus some space for what is called reminder. You define as a user the number of slots you want to use, and you also define the space for the reminder. When you want to when you want to add an element x, you compute its hash value with any hash function, and you split the hash value into two parts, the quotient and the reminder. And the quotient is going to be the address of x in the quotient filter. And the reminder is going to be what is stored in the quotient filter at this address. Alright? So for instance, if you want to add the element ACCA into your quotient filter, and imagine the hash value of ACCA is 001.00101. You consider that the first 3 bits are the address, so the quotient of ACCA, so at address 1001, you store the reminder. And there are some 3 bits we're going to see how they work. And the number of slots is defined by the user, as we said, and the maximal number of slots define exactly the maximal number of elements you're going to put into your data structure. But know that with a high occupancy rate, the insertion and the query of elements is going to be slower. And of course, the number of bits per slot determines the size of the reminder, and so the false positive rate. The main idea of a quotient filter, when you insert 2 elements that have the same quotient, so the same address, is to store the reminder of the new element, for instance, somewhere else in the filter. So this is somehow similar to open addressing in a hash table. The key idea is the fact that all elements having the same quotient are consecutive in the array, and all those consecutive elements having the same quotient define what is called a run. Imagine in this example we want to add a new element, GGAC, which has the same quotient than the first one we have been adding. So we would like to insert GGAC at this location, but this location is already taken with something else, so we are going to find the first location where we can put GGAC, and we put its reminder. And we are going to see how to do this and how to set up those 3 bits. Those 3 bits, what are they? So they are central. The first bit, so the red bit here in this example, is called isoccupied. It's extremely simple. If this bit is set to 1, this means that there is somewhere in the quotient filter an element whose quotient is equal to the address where the bit is set to 1. So in our example, here we know that there is somewhere in the filter at least one element whose quotient is equal to 1, because we have a 1 at address 1. All others are equal to 0. This means that there is no element with any other quotient in the filter. Okay, if you understood this, you can forget about this first bit. It's extremely simple. The 2 next bits are used to define somehow the start and the end of each run. The blue bit, so the second one, is called is continuation, and is continuation is equal to 1. This means that we are extending a run, and this is what we have in the previous example. Here the bit is equal to 1 because we are extending a run that started position 1. And finally the third bit is called isShifted, and if shifted is equal to 1, this means that we are currently in a slot which contains a reminder that is not at its what we call the canonical location, and the canonical location is where the we have this kind of situation. So for instance, here we have added reminder 11100, and 11100 corresponds to an element whose quotient was equal to 1, so it should have been here, but it's not, so we put if shifted equal to 1. That's it. Let's see what can be seen as situation with these 3 bits. Either they are all equal to 0. This means that we are in a non-occupied slot. Simple. The first one is equal to 0, and the two other one are equal to... So the first one is 1, and the two other one are 0. This means that we are in a slot that contains a reminder that is at its canonical location. And this is this situation. This defines also the start of a cluster. If this last bit is equal to 0, but the first one is equal to 1, this means that an element exists with this quotient I, but it's not at its canonical location. Right? We have shifted. This is not the case in this example. If the two last bits are equal to 0, and this means that we are starting a run, but this run is not at its canonical location. We are going to see some examples with this, and the same situation occurs if we have anything and 1, 1. This means that we are in a shifted run, or, well, we are in a run that is continuating, and this is the example here of address 2 for question 2. Okay, let's see some more examples. So I come back to an empty quotient filter, and I am going to add some elements one by one. I have added here ACCA as this was the case in our first slide. So when we tried to add ACCA, we end up at address 1 as quotient, and this address was equal to 0, 0, 0. What is not represented here is 0. And as it was 0, 0, 0, we are in a very simple case. There is nothing. We put our reminder here, and we set up the 3 bits to 1, 0, 0. There is now something here, and it's at its canonical location. Imagine now we want to add another element which has the same quotient. So we add another element with quotient 0, 0, 1. It should be added here, but here there is already something, so we are going to see where we should add this new element. We are going to see the procedure to detect where we should add an element. In this case, it should be address 2, and we are going to put this element here in this slot. And as we saw, we are extending a run of elements with the same quotient, so we are in extension, and we are shifted also. Okay, I'm going to add a third element and a fourth element, and the same process occurs again. The only thing we should take care about is to put the reminders in increasing order, so when we are looking for an element, we can stop as soon as a reminder is higher than the one we are looking for. So when I added, for instance, this value, I shifted the one I had put before, 11100, 0, 0, 0, 0 missing here, I think. No. Okay, no, it's okay. So in order to conserve these elements in increasing order. Okay, let's see now another situation. I want to add an element whose quotient is equal to 3, 0, 1, 1, but at this location there is already something. It's not empty. So what I'm going to do is the following. First, I put this first bit to 1. in any situation I do this because I know now I have an element somewhere in my quotient filter whose quotient is equal to 3, so I put this equal to 1, independently from anything other I am going to do. Then I have to find where I should put the run corresponding to this quotient, and I'm going to find location 5. We'll see a bit later how to find this location. And here at location 5, I store the reminder and I indicate that I start a run. So I have a 0 here. This means I'm not continuing a run, but I am in something shifted. So this code corresponds to 0, 1 here corresponds to I am starting a run, which is shifted from its original location. Alright, this is what I have just said, basically. Now I add again another element with the same quotient, 0, 1, 1, which should have been here, but here again it's already taken by something else. I find the start of the location of the run where I should put TTTA, so this element. Again, it's forced to address number 5, and here I see that I started a run. Well, I already started a run with this this quotient, so I'm just extending it as in the same way I did for the first 4 elements. So I have the same code here, 0, 1, 1, as the one I had here before. And I store here the reminder that should be 0, 0, 0, 0, 1. Sorry, I have... no, I say, excuse me. I put my reminder here in order to conserve my ordering of reminders inside this run. So now I have 2 runs in my quotient filter. Third situation, I'm going to add an element whose quotient is equal to 2. So as before, I put a 1 here because now I have somewhere in my filter something that has this quotient equal to 2. I find the position where I should put the run corresponding to quotient 2, and it falls to position 5. Again, we are going to see in the next few slides how to find this position 5. In position 5, I have already a run that starts, so I'm going to shift everything that starts here to the right. And this is what I do. I took all the green run here and I shifted it to the right, conserving the same bits and conserving, of course, the same reminders. And now this slot is empty and I can put my new element. And this is done. So now I have 3 runs in this quotient filter. And that's it for the examples. The only thing that reminds us to be understood is how to find the location of a run. So there are some simple solutions, some simple situations. Imagine the first situation. I'm trying to find the location of the run corresponding to quotient 0, 0, 1. So I'm going to check at this location what are the 3 bits. And here it's simple because the 3 bits are 1, 0, 0. This means that you are in a canonical location where the run you're looking for starts. So you know directly that the run that you're looking for starts at this location, and that's simple. Imagine you are looking for an element who is absent, well, whose quotient is absent from the quotient filter. So for instance, 101. 101 corresponds to address 5, and at this location, the first bit is equal to 0, so this means that there is no element in the quotient filter with quotient equal to 5. So there is no run corresponding to this element. That's finished. Finally, so this is the most complicated, but you're going to see that it's finally quite simple. Imagine we're looking for the run corresponding to element, to quotient 3, so 0, 0, 1. This is what we have done before in our example. You fall somewhere where you can see that there is an element which has this quotient somewhere in the filter, but it's not here because we are in a shifted run here. We have no 0, 0 at this location. This means that somewhere from 1 to 7, what we call here a cluster, because there are consecutive runs, there is one address that starts the run corresponding to quotient 3, and in this case this is address 6. How I'm going to find this? It's quite simple finally. Here I can see that I have 3 runs in this cluster. There are 3 colors, and we know that because we have 3 bits here which are called isoccupied, so the green bits, equal to 1. This means that there are 3 runs that are going to start somewhere. And we can, from, sorry, phone is ringing somewhere, from this location 3, what we're going to do is to scan left the cluster to until we end the cluster, counting the number of runs that have been seen from the start of the cluster to the address I am. So in this case we have 1 bit equal to 1 here, 1 here, and 1 here. So we know that from this location to the beginning of the cluster there are 3 runs that should be read before I find the start of my run. And how do I find the start of my run? This is again very simple. The start of a run can be detected by a 0 in the second bit. So for instance we have a run that starts here, a run that starts here, and finally a run that starts here. So the process is really simple. Count the number of isoccupied bit equal to 1 from the address I'm landing to the start of the cluster, and then go right, counting the number of slots where the is continuation is equal to false. And you count here, for instance, 3 bits equal to 1 of is occupied, and then you go right, decreasing a counter until it reaches 0, and in this case this would end up here at address 6, because we have read 3 is continuation bits equal to 0, and the start of your run is here at location 6. Alright? Okay, so if you understood this, you understood everything. And I just finished my presentation by, of course, seeing how to check if an element exists in the filter. This is finally what we are looking for. So to know how if an element exists in the filter, this is somehow the same process as inserting a new element. So we hash the element we are looking for. We find the run it corresponds to in the quotient filter with the process we have just seen in the previous slide. And once we have found the run where the element may occur, we scan the run from left to right, and if we find the reminder of the element we're looking for stored somewhere in the run, we return true, which means that there is an element which has the same hash values than the one we are looking for that is stored in the quotient filter. Maybe it's another element. It would be false positive, but still there is something. If we are still in the run, but we find a reminder stored bigger than the one we are looking for, we can return false, because we know that all the other ones are going to be bigger, and so we are not going to find the element. And if we get out from the run, so if we find a bit where is continuation is equal to false, we can return false because we are no more in the run and we have not found the element where we are looking for. Okay, so if we want to use a quotient filter to add some additional information, such as the amount of occurrences of an element, we can use extra bits. So in Squeakr, that is used in bioinformatics, 1 slot over 2 is used to store the abundances. So the filter is just twice as big as the original one in order to store the abundances. But we can think of any other way to add information to each slot by reserving some free space, for instance, after the reminder. Alright, a few words about the performances and the improvement. In this paper indicated here, some improvements have been made by coding something called rank and select quotient filter. I'm not going to go into the details here, but this enables better performances. And finally, it's a bit disappointed because without this improvement, the quotient filter here in blue is always worse than the simplest AMQ structure, which is a Bloom filter. So here higher is better in this figure, and so you can see that Bloom filter is always better than the quotient filter. However, hopefully, the rank and select quotient filter has better performances than the quotient filter itself, and if we have enough bits per element, the rank and select quotient filter becomes better in terms of false positives than the Bloom filter itself. Something independently from the quotient filter that is interesting to notice on this figure, and this is true for all approximate membership query data structures, is the fact that the Bloom filter, when you have a low amount of memory, so a high false positive rate, the Bloom filter is always the best data structure. So simpler is better in this kind of situation. And that's it. This ends this presentation.